Okay, good afternoon. It's me again. I'm gonna do a very, I think, creative session on, the topic around artificial intelligence and, well, what I would vaguely describe as artificial consciousness, maybe as a theme. Can machines think? We'll start with some philosophy, I think, or some wisdom, and we'll end up, you will see, with an exploration of logic, how computers work, and then we will not answer the question where does consciousness arise in this chain or in these rules that a computer applies. But we will hopefully make you think about it. So the Asian wisdom, it's a very old saying in Buddhist text. I don't know, you can Google it. I don't know the history of this thing, but it has been repeated by many thinkers, and it says something like, the eye that sees does not see itself. Um, or the eye does not see itself. Well, I would say the eye that sees other things cannot see itself. An eye cannot look at itself. Um, this phrase always struck me as being deep, and at the same time a bit self-defeating, because in the modern age, that today we could imagine maybe a robot or a computer that has a long arm and has a camera and can see itself. Or we can have two cameras, or maybe it can construct a camera somewhere, right? And with wireless, it can also get that feedback. And we know modern AI applications, they can analyze images, they can see structure, they can recognize, that's a car, that's a bicycle, that's a human being. So this computer, if you equip it with a good AI tools, maybe with ChatGPT, then you would have, I would say, an eye that or a mind, a mind is maybe a bit of a big word, but a system that is intelligent, seeing itself. Would that give rise to consciousness? Consciousness is a term, philosophical term, and so you need to define it. Consciousness, and especially self-consciousness, as we call it. While these are categories, and I mean categories in the terms of Gilbert Ryle, and so you should not make category mistakes. And how do you avoid category mistakes? Well, by applying, analytical philosophy and making sure that your concepts are well defined. So I will not say too much about that. But I said I want to start by asking questions. Think about that. What's the difference between how would you define consciousness, and if you have a definition, how would you define the difference between consciousness and self-consciousness? I think you would end up. I ended up with something like, okay, that's sort of in our language. We use a language to describe things, to make sense of stuff, and in our language we have, subject, verb, I do something. So we have this subject, action, verb, object structure, which is sort of built in how we make sense of the world. I think it's fairly easy to imagine that there's a artificially intelligent computer, a robot. I will talk about Asimov, the kind of robots that Asimov during the Second World War and after the Second World War imagined, the books he wrote on his laws of robotics. I mentioned it here. So we're now 2023. We could readily imagine that we could program a system that would sort of talk to us like ChatGPT does, and yes, gives the impression that it can clearly distinguish between, I or me as a subject that does or feels something, and a me and an I which is objected to some action or to some sentiment. So I would answer that again. I mean, I would take that. Yeah, here we have another example of where probably you should be quite positive in terms of what artificial general intelligence can do, and how we should approach it. But the basic thing is, I think in your definitions that you will slowly develop or want to develop, you will have to distinguish between intelligence, I think, and consciousness. The second aspect of conscious would be that, we would associate consciousness with what I refer to as existential experiences. Existential experiences are negative ones, pain, loneliness, but positive ones, happiness, or compassion, probably between the two. I just talked to my wife. Her sister has a cancer. It does something with me that is, not rational. I would say that is not intelligent. It hurts me. So there's a lot of stuff there that we would link to existential experience, and then the question is, could we program that kind of stuff into an artificially intelligent system? We could probably, and you see that already happening. In Japan, you have these little robots that keep people company. People start using ChatGPT, I think, as so kind of psychologist. Saw an article on that. Youngsters who chat with ChatGPT basically to relieve their feeling of existential loneliness. So yeah, that system seems to show then some compassion. Otherwise, it would not be so successful. But is it emulating, I would say, these existential experiences, or is it really experiencing them? Again, there you need to think about, what's the difference between experiencing something and just emulating. I think from our human experience, we know very well the difference between um, acting like we care or really caring. But that's a personal remark. Things to consider or to think about while you're doing this reflection. I'm just throwing questions here. Don't worry, I'll go into a lot more formal and I would say more scientific considerations later. But things you would think about when you ponder these questions is yeah, when we talk about existential experiences, how we make sense of the world. Yeah, the feeling morals are there. We talk about things that are used for a good or for a bad purpose. And we also know there's an additional distinction. We can do something bad, but with a good intent. That's how wars are justified often. We do something bad to do good. So the intent, but yeah, what's the intent? Can you program? This is the question I ask here. Can we program bad intent? Let me clean up my. Doesn't work. Doesn't matter. I wanted to clean up my notebook. But can we program bad intent? Well, I would say yes, and without much hesitation. Killer robots. Well, think of drones. They are real already now, right? And so these are programmed with, I would say, bad intent. They are programmed to drop a bomb where it hurts most. So my answer would be without any doubt, yeah, we can program bad intent. Does that make the machine bad? Well, you will say no, we cannot say that a machine is good or bad. Yeah, but you know what I'm talking about. People say that AI should be regulated and this and that. So there I'm rather conservative. I said, technology is basically morally neutral. It can be used for good or for bad purposes. So then you need to think about if you want to regulate it. Well, what are you going to regulate? the technology, or the people who develop the technology? That's a difficult question. I would, as a general advice, before I go into really formal stuff, advise that in these times, really, yeah, reread Asimov's books, in which he, develops imaginary situation in which you have robots interacting with humans, quite powerful robots that can do a lot, that are actually more intelligent than the people they serve. They're programmed to serve people, to help them. And there are three laws where, from time to time, boundaries are being reached and laws are in conflict with each other. And so that's very interesting. Another thing to consider, I would say, is this question: what does it mean to understand something? And related to that, I would say we have this, the Turing test. The Turing test is a test. Basically, if you talk to a machine, but you don't know if it's a machine or a human being, so there's some kind of screen or whatever between you and the other side, where there could be a human or where there could be a machine, and you talk and talk and talk, and after a while you need to decide, I'm talking to a machine or I'm talking to a human being. We know this test has been machines pass this test. ChatGPT passes this test with many people, but it depends. For me, it's not it's like irrelevant, because I used ChatGPT for two things, and I'm talking about ChatGPT 4, which can actually read files. When I chat with ChatGPT about computer programming, which language would be better, what are the competitive advantages of Go, what is Python very good at? Can you generate some Python code maybe that helps me to solve a matrix equation or whatever? It's excellent at that. So I cannot, it's better than a human being. But it's also where I say, like, no, this thing is so good at this that it can't be a human being, because a human being would need a lot more time to solve this problem. So I think the Turing test has become irrelevant. To be honest, Turing himself, as a computer scientist, it's like an informal philosophical test. It's not like the criteria for a computer to be a Turing machine. The formal logic with it, or other rules. Can a computer, for instance, reproduce its own system, or can, with one language? This is what I want to maybe talk about later. Bootstrapping techniques, as I call it, when building new or higher level languages. What are you going to use, or a compiler? Yeah, look at these things, think about it deeply. But I think the Turing test is not very relevant to answer, the questions we asked here. Can we go from artificial intelligence? I said that's really there, a rule-based system, to something we would vaguely refer to as artificial consciousness. Okay, let me now be a lot more formal. Yeah, I'll give you a very practical example. I'm not going to be long. You see here I have something terrible that's waiting for you. Yes, just before I go, because you may already switch off. So I actually tested ChatGPT 4 with 2 or 3 papers from mine, and this is my most popular paper. The probably is Matterwave, where I talk about wave equations, what they represent. Wave equations that are used to model, free electrons in space, and I talk about charge. It's a very difficult paper. I'm not so happy with it because it's not academic. I didn't Well, I didn't even try very much to get it published, but I asked ChatGPT for help to sort of structure, make this paper better because it has gone through 7 versions. And I realized while it was reading this paper, I mean, it read it very quickly. Yeah, it sort of is able to see what the structure is like. It's quite powerful at when I ask it bluntly, is do you understand the equations in it? Um, it says yes, but it's clear from what it does and what it says about it can parse the equations. It sees a symbol, a differential operator, or a wave function, and it can yeah, it can make the difference between a wave function, which is a solution, or a wave equation. So you can have intelligent conversations about that, but it doesn't clearly understand um, the paper and the points I'm trying to make. And you will say, well, nobody's probably understanding this paper. But that's not true because it gets a lot of downloads, and I'm a fast riser on this open research forum. It's got more than 14,000 reads, and I have a lot of good feedback on it. People who say like, okay, your style, your narrative is rather special. It's not academic, but you talk about points that are very valid. Especially because I think there is a bit of a feeling that mainstream theory is facing some issues, and maybe some simplifications are in place. I'm not going to make too much publicity for this paper, although I can recommend it. More reads is better. But the other one that gets a fair amount of downloads also is kind of interesting. The difference between a theory, a calculation, and an explanation. And in this paper, you will say, of course, I know the difference between a theory, a calculation, and explanation. No, a calculation is a calculation. A theory is something that may or may not be true. It needs to be confirmed by measurements. And an explanation is, something that explains things, establishes like causal relationships and whatever. The thing is, from a formal point of view, and we'll talk about formality, a theory and a calculation and an explanation can look the same. A calculation, then I mean sort of like, a formal derivation. We go from one theorem or a set of theorems, hypothesis that we formalize in a very abstract mathematical logic, and we apply the rules, the rules of reasoning and definitions of all these mathematical symbols. We expand them or we summarize them. I will show that in a moment, and it looks just the same as a theory. Because my theory, if I would formally explain it, I would say, well, this is what I assume, and you do this and that and that, and you arrive at that conclusion. And the explanation, well, yeah, it can look the same. You just apply it, and you insert some values in, the arguments of your functions, and you say like, hey, look, it works. So from a formal point of view, it's often difficult to distinguish, and I wonder, if at a deeper level, ChatGPT is consciousness enough or is intelligent enough to distinguish what for us is kind of an obvious distinction between theory, calculation, and explanation. So I'm not going to talk about that more. I'm going to illustrate it with this very simple example of what does a computer do when it does when it plays with numbers. And this may sound like a very stupid example, and it probably is, but I'm kind of proud that I found with it. This a computer, and when I say computer here in this case, don't think about in an output devices or a CPU that can do all kinds of operating system things. They at the basis of a CPU or a computer is an arithmetic and logical unit, which can do arithmetic and logical operations. And now the funny thing is, let's apply it. Let's do the arithmetic, an addition or a subtraction or a multiplication. Read about it, and the first thing you're gonna notice is that your view of there's a register and there's another register, and I put one number in register A, and I put another number in register B, and then there's another register with instructions, and it's going to add and put the result in a third register or in the first register. Really at the machine level, what you have are bits, right? Let's say we have 4-bit register, 4-bit computer. Only 4 bits. So we have the offset. This is the data array, or bit number 0, bit number 1, 1, 2, and 3, 4 bits. To store numbers, you would think like, yeah, we have positive and negative numbers, right? Yes, we do. So the normal representation you would think of is that, I have a 0 if I have a positive number, and I have a 1 in my most significant bit is the bit with the highest number, I would say, the position, and then the least significant bit is the 1. So I have a 0 or 1 for the plus or the minus sign, and then the highest number I can have is when all the 3 bits I have for my number, for my integer, are all 1. So the maximum I can do is, with 4 bits is code or represent numbers that go from +7 to -7, right? That's what you would think. I'm ruining my notebook, but it doesn't matter. Well, it doesn't work that way, actually, because, I said a machine works with bits, and these bits are 1 or 0. So it doesn't know what plus. It doesn't, an arithmetic and logical unit, you will say, okay, at the higher level, the machine will understand what plus or minus is. But then what you mean at a higher level, and where does that come from? A plus and a minus, well, it's a 0 and a 1. So how does a computer really treat, numbers, integers, signed integers? The thing is that computer scientists solved this problem and found an efficient way of doing that, because they also said, like, we have one more issue with these 0 and 1 that we use for a plus to represent a plus and a minus, is that we have 2 representations for 0. We have plus 0, which would be 0, 0, 0, 0, and 1, the plus 0, 0, 0. So that's kind of embarrassing or difficult, or, we have one logical value, 0, nothing, and we have 2 logical representations of that value. So we don't have a one-to-one relationship between logical values and logical representations. You will say, like, man, you're talking nonsense. But this is not nonsense. This is real. Numbers, integer numbers in a computer, will be represented by what is called the 2's complement of a number. And I took a lot of stuff from Wikipedia here, and I would really recommend you go and read it there. But plus 0 in decimal base here, set 6 in the decimal base 10. So in binary numbers, the base is 2. But we count because we have 10 fingers, I guess. We use the decimal base. So it would be represented by a 0, a 1 in the second bit, which is a value of 2, and then 4 in that bit, and then it's plus, right? It's plus. So we have 0, 1, 1, 0. That would be the logical representation of plus 6. Now, if we're going to take the 2's complement, which is what a computer really does, it's going to represent plus 6 like this. What it's going to do is, you say, oh, that's not a number, right? But no, this is how 6 is really stored in a register. It's a standard since 1985. It takes for each number, indeed, this sort of signed representation. The first step is this, that they're going to flip 0s into 1 and 1s into 0. And so we do that for all. 0 becomes 1. 1 becomes 0, 1 becomes 0, 0 becomes 1, and then it adds 1. And that's the difference between a 2's complement, as it's called, and a 1's complement. And so we have that. You will say this doesn't solve your problem of plus or minus 0 because you know you have 0, 0, 0, and this would also be 0 in a sign number representation. Um, yeah, yes and no. The thing which is very interesting is that the logic that's built upon that then and is in these two complement presentation, it's gonna move away from an interpretation where its most significant bit is a plus or a minus. Say the computer doesn't know what a logical negation really is. And so there's going to be logic in there that says basically any one at the number 4 bit is going to be interpreted as a minus 8. And we're going to do this addition, plus 0, plus 2, plus 0. And so we have as logical complement minus 6. I may have lost you, and I will be honest also, I'm probably not the best the best guy to explain this, and this is a very complicated matter. But this is where in 4 digits, we would represent the numbers 7 to minus 7 and also have a value actually for minus 8 unambiguously as these 16 possible configurations of 14 bits. And you will say the phase value, this is where here, the phase value of the lower 8 possible 4-bit configurations would be out of range values 15, 14, 13, 12, 11, 10, 9, 8. But we don't know that because, the machine works like this and says like, okay, we don't have out of range values, but this is sort of corresponds to the symbolic value of minus 1, minus 2. Again, I don't want to go into the detail of this because it would take me an hour to explain. But this greatly facilitates actually, arithmetic logic. And the thing is actually basically when you look at it, the machine doesn't apply any, logic or negation. It has only two logical operations. It switches 0, 1 bit to 1, or a 1 into a 0. And that's sort of, a succession of these mini micro instructions allows you to add numbers and subtract numbers, just another order of the same two bitwise operations that you repeat, multiplies and whatever. But the thing is basically, if you look at how an arithmetic and logical unit works, you cannot say really that it understands taking the negative of a positive number. So that would be the logical operation of a negation. No, it applies very mechanically, very small instructions, but plus or minus has no meaning at the machine level. The only things that have meaning, I would say, but it's really minimal, is a 0 or a 1 at a certain position in a register. So that's something I will let you think and Google and think about. But at at the level of an ALU, an arithmetic and logical unit, there's no way that a machine can sort of understand what it does. It just does things. And I said the only thing it can do is turn a 0 into a 1 and a 1 into a 0. Chatting with GPT, I'm not going to be long, but what I put here is Maxwell's equations. If you have any interest in physics, especially quantum physics or these kind of things, you will recognize it. Faraday's law, and so we have four equations of Maxwell. One works with and the electric field vector E, and the other one is the magnetic field vector. We know we have these are vectors. They have a direction, an x and a y and a z direction. So that's why they are vectors. Vectors also have a magnitude e. So we don't put the arrow. We have indeed what I said. ChatGPT knows these operators, the gradient and the divergence. and the curl. This is curl, and this is divergence. I'm not going to go too much into detail, but the one of the, I'm just going to show you one of the most beautiful equations, physical equations, because people sometimes wonder what is the equation of the world? Stephen Hawking. I know what is the equation of the world. Well, there's maybe a few, but in continuum thinking, Maxwell's equations, I would say there's one, and I'm going to show it to you. These four equations, applying suitable, and I could develop it, we're not going to do it. I did it actually this morning because I wanted to remind myself at how beautiful these things are. I can refer you to Feynman's lectures. You can write this set of four beautiful equations, and you have all the laws of electromagnetics, literally everything: electrostatics, magnetostatics, electrodynamics, where charges change in space, or charge densities change in space and in time. I'm talking about charge densities. This is the thing when you move to quantum mechanics, Maxwell's equations work with charge densities, not with discrete changes. But so when you have vector algebra, all of Maxwell's equations reduce to what is called here the D'Alembertian, which is sort of a four-vector equivalent of the Laplacian. This will not ring a bell. I will make it smaller because you might be interested to take a screenshot and be, I want to make sure that I know what this guy is talking about. So let me make it small, and then you can take a screenshot. I do the whole derivation here. I explain what these gradients, divergent, what they mean. And again here, this is like for ChatGPT. ChatGPT understands this thing. ChatGPT understands these formulas, and then it doesn't. It can parse them. It can really explain, these four equations. That's what's in there. We are taking the divergence, or we're taking the gradient of a vector, a quantity. We're taking divergence, or we're taking the curl. And it can also explain very well, like, okay, yes, I recognize that as Faraday's law. And then it will give you a nice text explaining, in not in symbols, not in formulas, but what it really means, what it does. Now, the same thing is that, so here this thing would pass the Turing test, I would say. It explains it, and then again, it would not pass the Turing test because you would say, like, wow, this is really in seconds that it comes up with, a very detailed explanation of things that I would probably need, 1 hour to go through the whole derivation, which includes a very nice concept, taking a gauge, choosing a gauge, and the Lorentz gauge. You might have heard that in field theory. You need to choose a gauge to simplify equations and solve them. But yeah, I would need an hour and probably more, and you would still not understand it. While I talked to ChatGPT and I've forgotten about these things, and and in a second or two, it will give that explanation. So it understands this, and at the same time, I've got something like is the same with what happens here. The computer applies, mathematically, mechanically, a set of rules to parse a text, a structured or a semi-structured text. Or often, your question may be completely unstructured when you ask it to ChatGPT, but probably it will acknowledge that and say, like, oh, this is not structured. I do not understand what you mean. And then it will ask you, do you mean perhaps this? It will rephrase your question. So, but yeah, it's going to be the same thing where you wonder, like, does it really understand it intuitively? I see when I look, let me go to that equation. Here, when I see Maxwell's equations, because this is equations that represent electric and magnetic field vectors in 3D space with a time dimension, there's dynamics in there. I understand these four equations and I can sort of visualize them because I've looked long enough at it, and yes, I did study quantum physics. I can actually go a bit further and think more abstractly about this way of rewriting Maxwell's equations, which is in terms of a scalar and a vector potential. When we have a magnetic and electric field vector, we have 3 space coordinates, so that makes like for 6 coordinates plus a time coordinate. So we have 3 spatial coordinates plus 3 other ones for the other vector quantity, and then we have a time coordinate. Thinking in terms of because electromagnetism is electromagnetism. When you have electric current, you're going to have a magnetic field. Magnetic field is going to generate an electric current. It's going to change the charge distribution. I can see the 4 equations of Maxwell, how they sort of give rise to radiation, how an electromagnetic wave propagates through space. And that's why, because I've looked at it so much, I prefer this representation in just 2 equations. And you'll say, okay, these are the 2 equations, right? Yeah, and they look terribly complicated. Yes and no, because I said when we then apply like a 4-vector algebra, we know relativity theory, I can think in terms of 4 vectors. 4 vectors combined. Let me show you. Yeah, here, this is a 4-vector. A 4-vector will combine a time coordinate and indeed then again 3 spatial coordinates. So the position for me is no longer a position in space only. I have my x, y, and z coordinate, but also a position in space-time because I have a time coordinate. And we have a Minkowski signature. I went through that, and so I understand what 4 vectors are, and I can sort of see how they play together and understand relativity theory, special relativity theory. So 4 vectors are easy to work for. I mean, are not easy to work with, but they make sense to me. And so the 4-dimensional equivalent of a gradient of a 3-dimensional vector operator, a gradient operator, or the Laplacian, which is the D'Alembertian. These 2 equations I had to represent Maxwell's equations, but using a vector potential and a scalar potential, which for me are more real, I said, because I can see that electric and magnetic fields, they're part of the electromagnetic force. One force, there's one force only. There's an electric force and a magnetic force, you will say, yeah, but that's kind of an artificial separation, which, it's like what Wittgenstein said, you need a ladder to climb, but once you're sort of on the roof, you can kick that ladder away and just enjoy the view. And so that's what happens when you understand these equations. You really enjoy the view. It's a more abstract way of understanding things, and I don't think ChatGPT can sort of appreciate that beauty of the mind. So, but make a long story short, I will end is I can rewrite these because that looks kind of terrible in something like this by an appropriate definition of the D'Alembertian, which is a dot product of the gradient, the 4 vector equivalent of the gradient operator with itself. And I said there's a choice of a gauge, but so I understand this symbol, and I also understand it's this operator. It's second order derivative with respect to time of a vector function or a scalar function minus the Laplacian, which is an operator which can also operate either on a scalar function or on a vector function. So I have this definition of the D'Alembertian, and I can apply it to a scalar function here, the scalar potential, and I can apply it to the vector potential, and it's equal to, in this case, a scalar. I apply it to a scalar, and in this case, it's equal to, some vector, the current vector. And current goes in 3 dimension and a bit more in the x or the y or the z direction. And so this shows how the charge density changes and in which direction it changes and what happens to it, not only in space but also in time, because it's a full vector and then it's divided by the electric constant, which we could relate to the magnetic constant. In case it's sort of a constant. Yeah, one important thing is to rewrite this. We use natural time and distance units, which is also something that I think ChatGPT, what is natural time and distance units? You will get an explanation, but probably you won't understand it at that kind of deeper level that you should understand to appreciate the beauty of what is finally then this equation. All of the laws of electromagnetic theory in this, we apply four vector operator, the D'Alembertian, to a four potential. I don't call it a four vector potential because we have a three with the vector potential is usually reversed for the three vector, the vector with three components. So we just call it a four potential. And well, to show, I know we have a full vector here, so there's no error. I thought I should put it's not working. A vector arrow, but no, we talk about four vectors. It's indicated by this little mu here. You're right, I'm reading my notes. Divided by a very fundamental constant of nature, which we can relate to speed of light, to magnetic constant, to the fine structure constant. It's all there. So if Stephen Hawking talked about the equations of the universe, well, this is the equation of the universe at the macro scale, I would say. With macro, I mean the level of an atom. If you go at the subatomic level, you realize that charges, talking about charge densities doesn't make sense. The electron is, or the charge is either here or there. It's not somewhere in between. So at the deepest level, at the smallest of smaller scale, nature is discontinuous, is discrete. So I would add Schrödinger's equation, but again, there I would say, if you really want to know, it is the Broadlee's Matterwave concept and issues where I solve all the problems of the, well, not of the world, but of our world view, at least in the area of what is real, what is reality, and what are we made of. So I'm gonna keep it at that because I realized this. I said it was a bit for fun. It's an experiment. It's also to ground a bit my thinking. I know it helps for me to talk when I want to do a paper, and I'm gonna do one on this idea of bootstrapping computer languages that can be used to construct or compile other programming, but basically construct some higher level symbolism, higher level languages to describe the world from a lower level. And that's in the end, to finish my talk, the question we need to think about it. Is there at some point, when we ourselves, we are, I believe in statistical determinism, so we cannot predict what's going to happen to us, in our personal life, but it is all deterministic. But it's statistically deterministic. We don't know the initial conditions. We don't know what's at the smallest of the smallest scale where a charge is exactly and when it's going to do what I would say, a quantum jump to, within a molecule, be closer to another nucleus or something. I'm talking very abstract here. Again, I would refer to my papers on physics, where one of them is that I'm going to show, maybe in the list here, a lot of stuff on meaning of uncertainty, but a more recent one. No. Whereas it is one on a statistical determinism and freedom of will, where I talk about that from a philosophical perspective, analytical philosophy, ontology and physics. It's not that. Oh, maybe it happens. Maybe I took it offline. But it would surprise me. So I have papers there also, logic and the quantum computing hype. I think quantum physics is understood often very poorly by those who talk about quantum computing, about logic and artificial intelligence. That's sort of more in what I've been trying to explain here in a series of papers I will here. The uncertainty principle, statistical determinism, and free will. Go to that paper if you're interested in these topics. I explain the uncertainty principle. Uncertainty is, from a philosophical analytical point of view, a very poorly defined. I don't think there's a clear definition of the uncertainty principle. And in this paper, I actually analyzed what Heisenberg himself wrote about it. He made a distinction in German. The language of science at the time was German. You know that. He distinguished between Ungewissheit, Unbestimmtheit, and Ungenauigkeit. And Ungenauigkeit is, if you measure something at a very small scale, you will interact with this thing. So you fire photons at an electron to determine the position of an electron. Well, there will be an Ungenauigkeit in that measurement because, the kinetic energy or the energy of these photons, it's going to interact with the electron, and it's gonna, that's what's referred to as Compton scattering, change the position, and in a way, because we don't know the initial condition of the initial conditions of that system, where exactly the photon is or where exactly the charge is, then there's no mystery. I recently had someone sending me a paper on the problems with the quantum measurement. No, there is no mystery there. And the other things do relate to what I refer to here as the concepts of statistical determinism, which I think is what our world is all about, and then free will. Free will is one that relates to this discussion because there again you have the question. I drink too much, or I smoke too much, or I have a bad habit, or I have this or that. What can I do about it? You will know what to do about it. It doesn't necessarily mean that you will do it. So that's the discussion on free will. What makes you do what you do? Hopefully, you will do what is necessary to do to lead a better and longer life. I try to do that, but don't think you can ground these things in physics. And there again, the discussion will be a little bit like this analytical process where I look at myself, analyze myself, and where I realize I have a habit I have to get rid of. Is that a conscious decision? Of course it is. But is it rooted really in a metaphysical concept like freedom, uncertainty? My answer to that is a categorical no. We do see here the emergence of intelligence, I would say, a rule-based system that comes to a conclusion given certain inputs. But yeah, perhaps it makes us human that we do not always do what is good for us, where a machine might do what is good for the machine. Is that good or bad? I don't know. There I need to refer back to this here. Read some good books that explore these themes, like Asimov's. And I would say, in 1968, this movie came out, 2001: Space Odyssey. I want to watch it again also, where a computer basically seems to develop some kind of emotional relationship. There was the movie Her in 2013, I think. So all these themes we are talking about have been actually, I think, better explored in art, in literature than in formal papers or stupid presentations like the one I am doing here. And with that, I will take my leave and wish you a very nice